Hello everyone, this is Mrinal Kanti Roy Chaudhuri. Today I am going to talk about the definition of constrained quantization and its comparison with unconstrained quantization for a probability distribution. First, let me tell you, if we say quantization for a probability distribution, what does it mean? What it involves? So it involves four different things: nth quantization error, optimal sets, quantization dimension, and quantization coefficient for the probability distribution. Constrained quantization means in the case of constrained scenario. And unconstrained quantization means those four things in the case of unconstrained scenario. That is when there is no constraint. The concept of constrained quantization has recently been introduced by M. Pandey and M. K. Roy Choudhury. Unconstrained quantization, which traditionally in the literature is known as quantization, is a special case of constrained quantization. After the introduction of constrained quantization, quantization now has two classifications: constrained quantization and unconstrained quantization. Let me now give you the definition of nth constrained quantization error. Let P be a Borel probability measure on Rk equipped with a metric D induced by norm this on Rk. R is a positive real number and alpha is any subset of Rk. Write VRP alpha equal to this expression. Those who are familiar with statistics and probability can easily understand this expression gives a kind of error which is called variance. In fact, VRP alpha is called the distortion error for P of order R with respect to the set alpha. Let Sj be a family of closed sets with S1 non-empty. So this is our constraints. Then for n belongs to n, the nth constraint quantization error for P of order R with respect to the family of closed sets is defined as follows. So we calculate all possible kinds of error, VRP alpha. And alpha is a subset of the union for j equal to 1 to n, Sj. And cardinal alpha lies between 1 and n when you are calculating nth quantization error. And take the infimum of all those possible errors. Now look at that. Here alpha is not any subset of Rk. Alpha is coming from Sj, union of Sj. This infimum is called the nth constrained quantization error. Now, does the infimum exist all the time, or is there any such alpha for which infimum exists? For that, we are always assuming for the probability measure P, we make the standard assumption that rth moment is finite. This ensures us that there is a set alpha in the constraint for which the infimum exists. Such a set alpha for which the infimum occurs and does not contain more than n elements is called a constrained optimal set of n points. So from this definition, we understood what is nth constrained quantization error and what is constrained optimal sets of n points. Now, we are going to give the definition of constrained quantization dimension. Let Vn, Rp be a strictly decreasing sequence. And write V infinity, Rp equal to limit of this. And look at that. V infinity, Rp is a non-negative number. Then the number drp defined by like this. is called the constrained quantization dimension of P of order R. The constrained quantization dimension measures the speed at which the specified measure of the constrained quantization error converges as n tends to infinity. For any kappa greater than 0, the number this, if it exists, is called the kappa dimensional constrained quantization coefficient for P of order R. Now, if you look at here, this expression, this limit may exist or may not exist. If it does not exist, then we defined limited infimum as d bar rp and d r bar p equal to limit supremum, which are called the lower and the upper constraint quantization dimensions of the probability measure p of order r respectively. For any kappa, the two numbers, this and this, are respectively called the kappa dimensional lower and upper constraint quantization coefficients for p. Notice that in unconstrained quantization, always v infinity rp equal to 0. So this number is always 0. Then all the above definitions of constant quantization error, constant quantization dimension, and the constant quantization coefficient reduce to the corresponding definitions in unconstrained scenarios. That is, unconstrained quantization is a special case of constrained quantization. Connection with other dimension of dynamical systems. In unconstrained quantization, it is known that lower quantization dimension lies between Hausdorff dimension and lower box counting dimension of the measure. Upper quantization dimension lies between packing dimension and upper box counting dimension of the measure. So here it is mentioned this and this denote the Hausdorff packing lower and upper box counting dimensions of the measure mu respectively. Under what condition on the constraints such kind of relationships hold for constraint quantization is not known yet. Some differences or comparison between constrained and unconstrained quantization. In unconstrained quantization, the elements in an optimal set are the conditional expectations in their own Voronoi regions. It is not true in constrained quantization. In unconstrained quantization, if the support of P contains infinitely many elements, then an optimal set of n points, that is called n means, in unconstrained case, contains exactly n elements. This is not true in constrained quantization. That means in unconstrained case, an optimal set of n means contains exactly n elements, but this is not true in constrained quantization. In unconstrained quantization, the quantization dimension of an absolutely continuous probability measure exists and equals the Euclidean dimension of the support of P. This fact is not true in constrained quantization. In constrained quantization, quantization dimension depends on the constraint. In unconstrained quantization, the quantization coefficient for an absolutely continuous probability measure exists as a unique finite positive number. In constrained quantization, the quantization coefficient for an absolutely continuous probability measure also exists, but it is not unique and can be a non-negative number. Because that it depends on the constraint that we are using in the constraint quantization. Here are the references. If anyone is interested to know more details about it. So this is our first paper, constraint quantization for probability distributions. And this is constraint quantization for the Cantor distribution. And there is another paper, constraint condition for uniform distribution. And I'd like to stop here. Thank you very much for listening.